breaks again. Today we'll have two speakers. Very excited to introduce the first speaker, which is Cosimo Bambi. Cosimo is currently a Shishide junior chair professor at the Department of Physics at the Fudan University, which he joined in 2012 after postdoctoral experiences at Wayne State University, IPMU in Tokyo, and LMU in Munich. He obtained his degree in Florence and his PhD in Ferrara, and his main research interest focused on theoretical and observational studies of black holes. And today we'll talk about a new generation of reflection models for precision measurements of accreting black holes.
Okay, thank you. So in this presentation, I would like to show you some effort to develop more advanced reflection models for precision measurement of accreting black hole, maybe for the next generation of X-ray emission. So this is the system that we want to study. We have a black hole with an accretion disk. The black hole can be a stellar mass black hole in X-ray binary system or a supermassive black hole in active galactic nucleus. The important point is that the accretion disk is geometrically thin and optically thick. So in this way, it can efficiently emit radiation. So this means that basically the gas in the disk has a high angular momentum, and the accretion, the mass accretion rate around a few percent to 20–30% of the Eddington limit. So the disk is cold because, as I said, it can efficiently emit radiation, and the thermal spectrum of the disk is normally peaked in the soft X-ray band for stellar mass black holes in X-ray binary systems, and in the UV band for supermassive black holes in AGN. Then there is this corona, which is some hot gas near the black hole and the inner part of the accretion disk. We don't have a good understanding at the moment of the corona. Presumably, the corona evolved with time. Two or more corona can coexist at the same time. Here there are some cartoons of possible corona geometry. For example, the corona may be the base of a jet in this post model. In the sandwich corona, the idea that the corona is the atmosphere above the accretion disk. Even the material in the Planchet region between the inner edge of the disk and the black hole can act as a corona. Here we have spherical corona, toroidal corona. Anyway, the important point is that, as I said, the disk is cold and the corona is hot. The temperature of the corona may be something like 100 keV. So for this reason, thermal photons from the disk can inverse Compton scatter of free electrons in the corona. And we have this Comptonized photon illustrated by the blue arrows in the cartoon. And the spectrum of a Comptonized photon is normally approximated well by a power law with an exponential cutoff, where the energy of exponential cutoff is related to the temperature of the corona, of course, because the photon can get energy up to roughly the energy of electrons. And the Comptonized photon can illuminate the disk. Here we have Compton scattering and absorption followed by fluorescent emission, and the result is the reflection spectrum. And this is, example of reflection spectrum in the rest frame of the material in the disk, which is characterized by some narrow fluorescent emission line in the soft X-ray band. In particular, you see the iron K alpha line, which is at 6.4 keV for neutral or weakly ionized iron, and it can shift up to about 7 keV for almost fully ionized iron. And there is no iron line if it is fully ionized. And then there is a Compton amp around 20–30 keV. The reflection spectrum of the whole disk, as seen far from the source, is blurred because of relativistic effect, gravitational redshift, and Doppler boosting because of the motion of the gas in the disk. And since every point of the disk has a different redshift, the total spectrum is blurred. And this is in the end, I mean, what we want to study. So X-ray reflection spectroscopy refers to the analysis of these relativistically blurred reflection features. And well, we are interested in this, in the analysis of this feature because well, the analysis of this feature can be used to study the strong gravity region around the black hole. We can study the accretion process around the black hole. We can measure black hole spins. And with this technique, today there are spin measurement for about 40 stellar mass black holes in the X-ray system, and more or less the same number of spin measurement of supermassive black holes in AGN. And it is essentially the only technique today to measure black hole spin with the spins of supermassive black holes. And I mean, you can also use this technique for testing fundamental physics, general relativity, but in general fundamental physics. So we want to develop a model. So in this way, you can fit the data and estimate the parameters the parameters of the system and understand the system. So this is the setup. We have a corona, a disk, an observer. So if we have a model of a corona, I mean, we can fire photon from the corona to the disk and calculate the emissivity profile. So basically how the corona illuminates the disk. And this typically involves, I mean, you have to calculate null geodesic in a Kerr space-time. The reflection spectrum, then to calculate the reflection spectrum in the stream of the material of a disk, we need to solve some radial transfer equations. And then we need to calculate the redshift image of the disk. So we can fire photon from the plane of the observer to the disk. And basically, we create this kind of image, and every point has its own redshift. Since at step 2, we had also the spectrum at every point of the disk, and step 1 also the intensity, let's say, of the at every radial coordinate in the case of axial symmetry. So in the end, here at the end of this calculation, step 1, 2, and 3, we have an image, and for every point of the image, every pixel of the image, we have a spectrum, which is redshifted or blue shifted with respect to the spectrum, the stream of the material in the disk. We integrate over the image, and we obtain the reflection spectrum as observed far from the source. So this calculation, however, are time-consuming, so they cannot be done during the data analysis process. So people in this field have basically followed this kind of strategy, which is called the transfer function. So the idea is to rewrite the spectrum as an integral, and inside this integral there are 3 key functions. And one is basically the emissivity profile of the disk, which is calculated at point 1. Another quantity is actually the reflection spectrum in the stream of the material of a disk, so where there is all atomic physics, there is no gravity, at least in general relativity. And then there is a third quantity, which is called indeed this transfer function, which is some not very intuitive function in the sense, I mean, this is not the first thing you do, but in the end, the transfer function encodes all the details about the relativistic effect. So the details of the calculation done at step 3. So in the end, I mean, the model for that analysis is a model that calculates this integral called 3-Fitz file. The Fitz file for emissivity profile, I mean, non-relativistic reflection spectrum, and this transfer function. And the integral is fast, so for this reason, you can generate many spectra quickly, and I mean, you can compare theoretical prediction with observation, find your best fit, I mean, and eventually the measurement for every 3 parameter. However, I mean, here there are some simplification. And so what we have done recently is to develop this model SHUA. This is just the name of the model. The first author is Timur Beck Mirza, is one of my PhD students at Fudan, and it was basically developed some existing model developed by previous student, and we also need a reflection model. In particular, for the moment, we are using Reflions, which is the model developed by the group in Cambridge by the group of Andy Fabian. But in principle, we can also use other models. So, I mean, this is not a model for data analysis for the moment. The model we want to develop a model for data analysis, but for the moment it is too slow. So it can calculate a reflection spectrum with many astrophysical ingredients, but it is too slow for data analysis. So at the beginning of we can specify the spacetime. Typically assume a Kerr metric, and so you have only two parameters, the mass and the spin of a black hole. You assume the properties of accretion disk. We use the Novikov-Thorne model, but potentially, I mean, we can also consider extension of this model. We have to specify the electron density of a disk, and in principle, we can also use some non-trivial electron density profile. And we need to specify the properties of a corona. In the simple case, we have a Lampos model, in which the corona is just a point-like source above the accretion, along the black hole spin axis. But even in this case, I mean, we can generalize that. And I mean, basically, this is the model. I mean, go step by step, step 1, 2, 3. That I mean, I showed you before. So if we know the properties of a corona, we can fire photon to the disk, and we can calculate how the corona illuminates the disk. Then at every point, well, actually at every radial coordinate, we calculate the reflection spectrum. Here we need to solve the radial transfer equation. We cannot use. I mean, at this stage, we can also use the table of Reflions auxiliary, but actually, if we want in the steps after, basically we need to solve the radial transfer equation, so we need the code. And then we include the effect of returning radiation, so some radiation that is emitted by the disk and returned to the disk because of a strong light bending at the black hole. And in this case, we need to recalculate the reflection spectrum. This is because it is not a nonlinear process, so it depends on the actual incident spectrum. We cannot sum up different. I mean, if the result of the sum of incident radiation is not, I mean, equal to the. I mean, we cannot sum the reflection spectrum with incident radiation. And we need to iterate this for a few times, typically 3-4 times. And we can do also the same for the thermal spectrum. In the case of supermassive black holes, actually, this is not important because the thermal spectrum of the disk is in the UV band, so I mean, it's not here for, it doesn't play a role. But in the case of stellar mass black holes in X-ray binary system, the thermal spectrum is in the soft X-ray band, so it affects the reflection spectrum. At the end, we have a spectrum at every radial coordinate of a disk, and okay, we use a standard ray tracing technique to calculate the reflection spectrum of the whole disk as detected far from the source. And well, basically we simulate some observation of bright galactic black hole with no star using this SHUA, and then we fit the data with standard reflection model for data analysis. And I mean, we see that there are some unresolved features in the sense, I mean, the quality of the fit is not good. And in other words, I mean, basically, I mean, it is with the returning radiation cannot be reabsorbed in a redefinition of the emissivity profile, because, well, because in the end the spectrum is different. Because a normal reflection model for that analysis always assume that the incident radiation is a power law with an exponential cutoff. And on the end, in the case of a return radiation, or even the return radiation of the reflection spectrum, or the return radiation from of the thermal spectrum of a disk, have a different shape, and therefore also they produce a different reflection spectrum. And the difference is larger for very fast rotating black hole when the corona is close and compact to the black hole, which are also the case in which we can obtain more precise observation. So how to develop a model for that analysis? Well, this is actually sort of a work in progress. For the moment, we have just some ideas. And we cannot use the standard framework because, well, for example, I mean, these key quantity are pre-calculated and tabulated in some FITS file. And the FITS file of the non-relativistic reflection spectrum is already quite large, even if in the end the incident radiation is only power law with an exponential cutoff. So if we want to, I mean, the FITS file is already 1 gigabyte, which is roughly the maximum size for normal RAM. And I mean, if we wanted to use the same technique, I mean, we would have very large FITS file, which would be unfeasible, especially for a normal computer. So we are considering a different approach to create a model for that analysis. The simple scale is just to write to construct a library, but since here there are many parameters, I mean, it would be not so straightforward. Basically, typically, even in the simple case, you have 13, 15 parameters, and I mean, if you consider more complicated coronal geometry, 20 parameters, I mean, it could be a mess. And if you want to improve some part, you should reconstruct the library from the beginning. So this does not sound to be a smart idea to create a model for that analysis. We can use some machine learning technique, but well, the number of parameters is still very large. Even in this case, the idea would be to construct a small library and train some neural network to predict the reflection spectra. But as I said, I mean, even in this case, probably the library is would be too large. And so what we are thinking is just to use some strategies similar to the current strategy, in the sense to split the problem in smaller problems. And I mean, with different parts, some parts are keep some part of a current approach and introduce some new ingredient. And the idea, I mean, is sketched in this cartoon. So basically, we can specify the space-time geometry, the corona, the disk, and the disk can, I mean, this necessitates just some script or a small program to calculate the direct incident radiation from the corona and the thermal spectrum. And in the end, I mean, the returning radiation basically in the chirometric depends on one parameter, which is not a problem. So with a small program, we can just consider for every disk, I mean, we sum over all the point that we know the disk, the origin of the returning radiation. And then what we are thinking about as a new ingredient is to calculate the non-relativistic reflection spectrum at every point. We cannot solve the answer equation because this is too time consuming. We are thinking about a neural network, and just to train a neural network in which you have as input the incident spectrum and as output the reflection spectrum. Probably we need to iterate this a few times as we are doing now with ChUA. And then when we have a reflection spectrum at every non-relativistic reflection spectrum at every point of the accretion disk, presumably you can use the standard technique of the transfer function, which is just to integrate over the disk, and you obtain the full reflection spectrum in this way. This, as I said, this is just a sketch about our plan, say, for the next 2-3 years. And in principle, I mean, we can also include, I mean, more complicated, more sophisticated models. For example, I mean, at some point, we can replace the Novikov model with a GIMHD simulated thin disk, but I mean, this is not our priority. And yes, I think I can stop here. Thank you.
Questions? So there is a question online by Dan Schwartz asking what specific observation could in principle contradict a general relativity prediction?
I mean, in the case, the simplest test is to test the Kerr metric in general relativity. And if you believe in standard physics, the spacetime around an astrophysical black hole should be described as a Kerr solution. You can test the Kerr hypothesis. In this case, you need, I mean, this is actually something that we have done in the past. In the case of when you calculate the transfer function, you need to calculate not the transfer function of the Kerr spacetime, but some more general spacetime in which there are some extra parameters, and then you can quantify these extra parameters. This is the simplest test. Otherwise, you can still work on the transfer function and try to test the weak equivalence principle. In the sense, according to the equivalence principle, all particles follow the same trajectory in the spacetime. You can test, for example, if, for example, you may have a situation in which photons follow the geodesic of the Kerr spacetime, but the particle in the disk do not, or the opposite. This kind of test. Even you can also change the atomic physics in the strong gravitational field. In the case of general relativity, atomic physics in the strong gravitational field is the same as atomic physics in our laboratory on Earth, simply because there is only the metric tensor, so you can always perform a coordinate transformation, and locally the non-gravitational laws of physics are the laws of special relativity. But in other case, I mean, this is not true. I mean, in some extension of general relativity, you modify your calculation of the radiative transfer equation. I mean, you need to construct a model, and then, I mean, you typically have some extra parameters. You fit your data of some black hole with a very strong reflection feature, and you can test the general relativity.
Do you think we are sensible to these parameters with the data available today, given that already,
yes,
as you mentioned,
we did. I don't have here the plot with this constraint, but actually they are the constraints we can obtain with this technique are a bit stronger than current constraint with gravitational waves, and significantly stronger than current constraint with black hole imaging.
So how degenerate are those with the geometry, which you've only got one geometry here, right? And you mentioned it.
Yes, of course.
Possibilities.
Yes, of course you need to consider many geometry and see if there are degeneracy. I mean, if you use only the thermal spectrum of a disk, for sure there is a degeneracy and you cannot get constrained, because the thermal spectrum is a very simple shape. It's just a black body, a multi-temperature black body spectrum. In the case of X-ray reflection spectroscopy, you need to select the right sources and the right spectra. But if the relativistic signatures are strong enough, you can break the parameter degeneracy.
Any?
I have a similar question on the geometry. Is anybody, Andy's group or anybody else working on new models of what the lamppost might really look like? Because there's so many parameters. I think you mentioned at the beginning, didn't you, that you were using a point source model?
I mean, this is in the case.
A way to begin, but it's obviously
yes.
complicated.
I mean, actually, if you go through the publication in the literature, there are also studies in which people don't use the lamppost model. Lamppost model is just the simplest model, and if you don't want to make assumption about the space-time geometry, typically you employ some phenomenological emissivity profile, like power law, Broken power law, twice Broken power law. There are also some models for data analysis in which you can have a more complicated geometry than Veillon post. You may have some disk-like structure, ring-like structure. There are publications in the literature also claim that if you use a broken power law or twice broken power law, I mean, you have enough freedom to basically mimic more or less most of the coronal geometry. So if you don't want to have, I mean, to make any assumption about the coronal geometry, you assume this power law, broken power law, or twice broken power law, you should be able to mimic more or less all the coronal geometries. Then, of course, it depends on the quality of your data. If presumably the quality of the data is very good, I mean, this is not enough.
No, there is no time for an extra question. I'm sorry about that. But I'm sure that Cosimo has still plenty of time.
Yes, of course.
So I encourage everybody to check the spreadsheet and we'll. As soon as everything is set up.
It's not here, the mic, and here?
Yeah, you
Okay. And let's try and make these things disappear. Yeah, thank you. Hide video panel. Hide something else. Loading controls. Okay. Get rid of all this, get rid of all that. Okay, so thanks. Right, so I do a lot of things. I'm going to talk in particular today about fast X-ray transients, which is one of these sort of fields. So in particular, the idea is to explore the population of extragalactic fast X-ray transients, which is a relatively new area, and we've sort of found that there's sort of a hidden population that's quite large. So this is work done by my former graduate student, Jonathan Corolla Vasquez, in collaboration with various people who you've probably seen or know. So to sort of start off, we have a sort of vast array of X-ray transients out there, and these can be from planetary atmospheres where you have storms on, say, the pole of Jupiter. We have stellar flares, right, that are from our sun, from magnetic reconnection events. We have X-ray binaries and accretion onto compact objects, as you might have thermonuclear explosions, magnetic reconnections, relativistic beaming. So there's a whole slew of potential transients that might occur from various X-ray sources. You have supernova, and when they go off, as the shock breaks the surface, you might see supernova shock breakouts, and then later on ejecta CSM events. You have tidal disruption events, and some of those may generate X-ray emission. You have longer gamma bursts, which have jetted emission, again from sort of young stars that breaks out. You have short gamma bursts, so mergers of neutron stars that might again create some X-ray emission and a kilonova. You may have some events associated with AGN, some sort of accretion events which disrupt very fast, or relativistic beaming. So all of these things, right, we might see in the X-ray sort of variability landscape. And so we're trying to sort of make sense of some of these things. And of course, there's the unknown. There's other things that we may find that we didn't know of before. And of course, many of these things, because they are related to compact objects, there's a connection to gravitational waves and to multi-messenger physics. Okay, so that's my sort of broad motivation for what we're doing. Just to sort of crystallize that, this is the sort of landscape in terms of the time scale of the X-ray event or the optical event, the X-ray luminosity, and then the optical counterpart luminosity if it has such. And so in particular, I'm going to focus on this area here, which I'm going to dub fast X-ray transients, basically X-ray transients that are occurring in less than a day. This is a super arbitrary definition, but nonetheless, it groups things relatively well. And then I'm also going to focus on mostly the extragalactic side of things, not the galactic side. And of course, that kind of cuts around the luminosity range of above 10 to the 40 ergs per second. And so you have, as I mentioned, you have the supernova shock breakouts, the tau disruption events. You have gamma ray bursts and X-ray flashes and subluminous things. Occasionally, you can actually get soft gamma ray repeating giant flares from magnetars, but these are very, very short. Okay, so that's more or less the sort of landscape that we're trying to probe. And the other thing to sort of note is I'm trying to, in particular, study objects which we see once and we don't see again. So they're not necessarily repetitive objects, or they don't necessarily have a constant value and then they flare up. Right. Okay, so giving you a little bit of a brief history of sort of how we've characterized fast X-ray transients to date. They've been seen in a number of past missions. Many of you have, well, some of you have worked on those missions and probably remember some of these fast X-ray transients. And so there's, actually a decent amount, almost 200 that have been detected in sort of the I'll say ancient times of X-ray astronomy, the sort of pre-2000 date. Largely, these had poor localizations. They were largely done with archival searches, so you couldn't necessarily find counterparts that were contemporaneous with them. In general, there was no division, because of the poor localization. There wasn't any real obvious division between galactic and extragalactic, or between persistent and one-off events, because there wasn't much follow-up or localization. Right? This is the sample, and so they look pretty extragalactic. This is galactic coordinates, so there's not a huge, a grouping of them along the galactic plane, for instance. But nonetheless, we could be contaminated by flare stars in the upper disk and things like that. And some of them could have been, sort of confirmed gamma ray bursts. So the sort of number counts, as it were, goes roughly as the inverse of the fluence, which is the sort of flux per second. And so this is sort of the regime where Einstein and Rosat, and so the new X-ray telescopes would sort of probe in this regime. So that's what we knew prior to 2000. After 2000, of course, Chandra and XMM and eventually Swift launched, and they provided much better localization. So one of the first objects that was found in sort of the modern X-ray times was this X-ray transient associated with supernova 2008D by Soderberg et al. And they, of course, this ended up being associated with a young supernova. They were actually trying to observe this object at the time and just happened to get this one in the same field of view. And so you see a nice sort of X-ray, a sort of fast rise exponential decay over a few hundred seconds. And so this was considered to be a shock breakout from the surface of a relatively compact star. So later, but actually this event occurred before, Peter Jonker and his collaborators found this sort of crazy event, which had some precursor mission, huge flare, which actually could be resolved into this weird looking structure here, and then a sort of plateau that was higher than the precursor mission, and then the observation stopped. This was found in the archive. No one went out and followed it up, so we don't know what happens afterwards. It happened to be in an observation of M86, and Peter nominally sort of said, oh, maybe it's associated with this faint tidal tail that is seen, but it wasn't really clear. And so he initially associated it with M86 and gave it a luminosity of 6 times 10 to the 42. and thought it might be basically an intermediate mass black hole with a white dwarf that had been tidal disrupted. And that was his sort of argument. More recently, deep imaging from Gran Canaria telescope found a faint host here at G of 26 magnitude. And so this might actually be a distant object that was just serendipitously observed near M86. A similar object was found by another person in Peter's group, and this was published as Glynn et al. And so again, you see this very sharp spike, this plateau, and the sort of main peak is now not double humped anymore. The deepest imaging, again from Gran Canaria recently, finds no host to a magnitude of about 26 or so. And so again, not clear what this was. It lies in the vicinity of a cluster, but it's not, obviously near any bright galaxy. And so it's sort of unclear what distance it's at. Then my foray into this came when we were involved with the Chandra Deep Field South and pushing it from 4 to 7 megaseconds. And in particular, we were getting the data and actually looking at the data as it came, basically like 1 day, 2 days after it was taken. And we ended up finding 2 X-ray transients in this data. And this is what they look like. We made nice press releases with the Chandra X-ray Center. And they were both relatively quick objects that lasted sort of maybe 5 to 10 kiloseconds. And so their light curves look like this. So this was the one I found. So it had a rise and then an exponential decay. This is the one that Yongquan Su found, which had sort of a plateau and then a decay. And we're just comparing them to a bunch of GRB light curves, long and short GRBs, a couple of X-ray flashes, a TDE here, and this is the 2008 D shock breakout. So you can see they're pretty luminous. They're at the faint end, though, of what we'd expect from gamma ray bursts. We don't see any, really bright emission early on, which you would associate with a gamma ray burst. And so in general, would have to be something that was less luminous and maybe didn't give off that initial burst. So we could have a failed jet, we could have something else, maybe a magnetar, maybe it's intermediate sort of jetted emission from a TDE, sort of unclear. For XT1, we actually had optical constraints that were serendipitous. So the VLT happened to be observing that same night for other reasons and took an image, pre-imaging for a spectroscopic survey that put a very, very faint limit on the optical counterpart, so about 25.7 or so in R band. And so it ruled out, these are sort of bins of optical afterglows for GRBs. And you can see we can pretty much rule out from this observation the vast majority of them. So it clearly was something different from a normal GRB. And we got some later time data, and we were sort of able to rule out at least a longer term counterpart as well. So again, this sort of points to something that may be off axis, maybe subluminous, a little bit different from the normal sort of objects. And so the idea that we had was, well, we found 2 objects in 7 megaseconds of data, right? And so that would suggest that the Chandra archive is just filled with these things, because you observe something like 20 megaseconds a year for 20 years. We should have a few hundred. So we said, well, let's go. And so, also XMM should have the same sort of numbers. So the goal was really to try and identify all of these types of objects. And maybe we would find some objects that were like the gravitational wave source 170817 that were just in the archive. So that was kind of the goal. If we focused on Chandra because it had better localization than XMM, but nominally we could do the same thing for those. The idea was then to characterize the concurrent emission if we could, and to study their host galaxies if we could find them using new and archived data. And then ultimately we wanted to compare these to all of the wonderful gravitational wave sources that LIGO Virgo was going to detect. We were hoping to have at least 10 of them, given the sort of optimistic numbers. At this point, we still only have the 1, but nonetheless, it's still a sort of future goal. So Jonathan published a couple of papers on these events here. So the idea is very simple in terms of methodology of detection. We basically just cut the data set into parts and look for a transit. So we use already detected sources from the Chandra source catalog or from our own sort of detections of the stacked data. And then we go back and look to see if it was actually a transient or not. And so we searched something like 450 sources, 450,000 sources, cutting out the galactic plane because we didn't want contamination from stars. And so we ended up searching about 260 megaseconds of data, or roughly about 850 square degrees of sky. And again, our aim was to sort of find these similar types of objects. And so we required a 5 signal Poisson limit on these sort of constraints. We split the data in various ways so that we didn't miss any objects and so forth. And additional criteria, if it had extra observations, we checked those. And in general, about half of our initial candidates from flares were rejected because they had an extra observation before or after, and we saw it again. And so we removed something like 50%. We then checked Gaia and other large catalogs for stars, obvious stars that had proper motions or parallaxes or something like that, or point-like. And again, that rejects something like 60% of the stars. And so we whittled down the sample, and then we went to deeper catalogs and tried to whittle it down some more. Finally, we checked for instrumental effects. Chandra has a dither, so you can see that the photons actually move around on the chip with time. And so we ended up with a sample here of about 20 odd sources. You can see them in black here. These are the count distributions, so relatively faint sources. They only have sort of tens to maybe 100 counts in most cases. 1 or 2 have 1,000 counts. So it's you don't have a lot to work with. We then also checked where available if it had any contemporaneous sort of data that could find, you can see a counterpart in another region. So this is the final sort of sample in red here. These are our sources. They're pretty extragalactic. The blue ones were the ones before we did our sort of final vetting. And so Jonathan published 22. We since have imaging in the infrared and removed one of them because it ended up being a star that we hadn't selected out before. So we had 21 candidates. We recover all of the past known ones, which is good. And I also note that Alp and Larson published a catalog of 14 objects that they found from XMM that I'll sort of I'll show some of the results or comparisons with that. We've rejected 2 of those already from deeper imaging that we have. So these are the candidates, and so we looked and tried to find the counterparts, and 5 of them actually ended up being in local galaxies. Not only were they in local galaxies, but they ended up being in star-forming regions or consistent with star-forming regions. Right, so stellar cluster. This is one of these, I think, has an H-alpha image. Let's see, here's the H-alpha image. So you see it's really strong in H-alpha, but sort of hidden in other ones. And so it's kind of weird and interesting that at least, okay, thanks. 4 of the 5 sources are consistent with star-forming regions in galaxies at 4, 6, 10 megaparsecs. So clearly that's one subset of the sources. A 5th one, this is Sen A, and this has a counterpart in the F814 band, maybe a faint one in the F606. We don't have near-infrared imaging, so we think this is a globular cluster. So one of them may be associated with an older star population in the globular cluster. These are the light curves of these objects, and here I show the Yonker object in its local form. I'll show it again in its distant form later, just to sort of show a comparison to our sort of library of potential objects, extragalactic. These are all much lower luminosity, and they have a sort of variety of light curve shapes. Our distance sample, there's now too many to really go in and dig into. I just give a range of the properties here. So they have a huge wide range of magnitudes, a pretty wide range of redshifts and stellar masses and star formation rates and offsets and hence luminosities. To summarize, you could look here. This is the R-band magnitude distribution of the sources, and the redshift for each of these are redshift constraint. So most of the bright ones we've now got decent photometry of and have redshift constraints, if not the spectroscopic redshift. Below the sort of ground-based limit, we have a ton of objects where we really need space-based imaging or really, really deep 10-meter imaging still. And then a few cases we have actually JWST imaging, which has nicely pinned these things down. And you can see that they're at quite a high redshift at this point. This one's a spectroscopic one, this one's a photometric one. So these are the two J2ST objects. So you can see this is a relatively sort of faint object with maybe a tidal tail, or maybe it's a cometary dwarf galaxy. It's sort of unclear. Here we have another one. This is the localization. And before it was associated with this object and it had an incorrect redshift. And so now we have the correct redshift, and it looks like it's associated with the obscured region of that particular galaxy, that redshift 3. And so for the objects where we could actually get some sort of constraints on the SEDs, we fit them for their stellar mass and their star formation rate. We put them in the main sequence of galaxies, star-forming galaxies. And so these are these objects here, and we show the local Sloan objects here, and then hosts for various types of supernova, superluminous supernova, long gamma burst, short gamma burst, and the tidal disruption events. And so in general, they seem to have a decent overlap with the long gamma ray burst population, maybe somewhat with the short gamma ray burst, maybe somewhat with superluminous supernova, not so much with the others, but this is also because they're at higher redshift partially. Yeah, so that's at least the host constraints. Looking at the light curves, they show a variety of properties. So some of them show broken power laws like XT2, which I showed you before. Some of them show rise fall like XT1. Some of them just show normal sort of power law declines from the start. 5 of them are complex. I'm not showing all of them here. And so you can see that you have some that really are sort of unique in this sort of parameter space. Some that probably maybe are just a lower luminosity version of the gamma ray burst. So it's sort of unclear. In terms of their spectrum, we can't do much with 100 counts. So we have hardness ratios, and so in general, this is the sort of sample, and you can see here the sort of the range that short gamma ray bursts might have. This is the range that the XMM sample has. So in general, they have sort of modest, soft hardness ratios. If you make an estimate with a photon index, again, their sort of estimates are sort of between 2 and 3 typically. And so putting this back on this plot, we don't have redshifts for that many of them, or strong redshift constraints. And so you can see sort of the lower redshift constraint here, and then if they're at higher redshift, they move up this way. So we have the local sample here, which is in a weird, unique area, which is not really where you would expect SGR flares. Maybe they're associated with some sort of ULX, some sort of compact object magnetar. It's not very clear. For the more distant ones, right, they are sort of in general at the very bound for shock breakouts. We can generally rule the shock breakouts out. We can't necessarily rule out various exotic types of sort of lower luminosity GRB or even jetted TEs. And so those are still open. In terms of the event rates, coming back to this is the original fluence, or so the number goes as the inverse of fluence. We see that breaks, and we have basically a slope which is now -0.5 rather than -1 with the fluence. And so it flattens out, but it's still upward sort of trend. And so we can now make these predictions for new X-ray telescopes, which are pretty robust. We can compare these to the different populations. So the gray band is the overall sample, and these are two sort of extreme cases. And in general, if we correct the luminous, the long gamma ray bursts for their beaming factor, we get something which is kind of comparable. If we correct the short gamma ray bursts for their beaming factor, we're still a little bit on the low side. And then TDEs, if we look at the TDE, the IMBH TDE rate, it's very, very tiny compared to the numbers we see. And so either something needs to change with those estimates, or we don't have too many IMBH TDEs yet. Okay, so the conclusions, I'm running out of time, so I won't really go into these, but I already sort of summarized them. We have a mixed bag of origins for the nearby objects, and we have a range of properties which are not necessarily all similar for the distant ones, and so there's really, I don't think we can sort of pin this down yet, unfortunately, but we do have some reasonable cases of this. And so near term, obviously getting deeper imaging for the objects which just have upper limits. We would like to go and search for these things in XMM and Swift. We think there should be a decent amount in there. It was sort of puzzling why the early attempts didn't find any, but there was a recent paper by Ruiz where they looked at a very small subset of the fields and found an extra fast X-ray transient in just like 6 or 7 fields. So there may be a lot hidden there. For the objects which have sort of similar traits, we could apply more complex X-ray models to the light curve and the spectra to see if they match those. Of course, there's eROSITA, which just had a data release. It's of course not observing at the moment, but it has 4 epochs. One might hope that there are some detections in there, but the way that it observes is such it may be very difficult to tease those out. And so there's only been essentially one fast X-ray transit that's been announced so far. So it's unclear. Einstein probe launched earlier this month. Einstein probe's a Chinese mission. It has a huge field of view, but is not that sensitive. The benefit of that is, of course, that you're going to find all of the bright, rare objects. And so we expect something like 10 fast X-ray transients per year. They're all going to be at the bright end, so we can actually follow them up for a decent amount of time, say with SWIFT or with XMM. And hopefully they have counterparts in other bands, and so we could find those with ground-based or space-based telescopes. So that's kind of the near future for this. So I'll leave it there. Take any questions. Thanks.
Okay, thanks. Really nice talk. Oh, so many questions. Okay, let's start.
All right. Very nice stuff. I was wondering what happens looking at kind of sample properties. I mean, here you have a 5 sigma cut, you want to do your optical identification, so you have a clean sample of that. If you relax this 5 sigma, you go to 4.5, 4, 3.5, say in the Chandra catalog, where the position is good, the sensitivity is good, what do you find?
We don't know. We didn't want to go too bit. So one of the things, of course, is that we started with the Chandra source catalog, which actually has like it's a 10 sigma effective cut, right? It actually is pretty conservative. So in that sense, I think that might limit how far we can go down. We'd have to go back and do a less sensitive sort of thing. In theory, we should be finding them. The difficulty will be in sort of teasing out, that they're there, but it's possible. We will have difficulty in sort of the positions will be worse potentially. Yeah.
Very interesting. I'm curious. I know it's a small number of statistics, but do you see any correlation between the luminosities and, say, the decay time scale, or anything along those lines?
Yeah, I mean, we haven't. I think the statistics are too bad. Or even like, how do you define some of those things? Ends up being a little bit tricky for these because they don't have that many counts in the faint end of things. And so we haven't seen anything obvious, but we might be able to tease something out of a subset of the sources. It would be better if we had the XMM sample. If we could have 40, 50, 60 objects, then we might be able to see.
Yeah.
Very nice work. Just follow up on Pepe's question. I'm pretty sure if you put that significance level a little bit lower, you will probably find at least a few more.
Yeah.
But my question is about so if some of your candidates you think could be electromagnetic counterparts to magnetar forming neutron star mergers, if that's the case, do you expect to see? And I know that for most of these objects you have only a few counts, but do you expect to see a particular profile of the light curve that kind of matches any spin down of the magnetar, things like that? And second, could you measure? Do you expect to see any spectral changes during the transient that you could at least possibly measure for some of these objects?
In general, we can't do much with the spectral evolution as a function of light curve because with 100 counts, it's really tricky to start to split that up and start to really get any reasonable constraint. So, we did publish something for XT2 that had this potential sort of softening. We see that in a couple of cases, which might argue for some models over others. In general, for many of them, with 50 counts, no, it's just, you don't have that constraint, right? You barely have one spectral constraint in your average and then over the entire, like, so hopefully for the Einstein probe objects, we're gonna have much better constraints on a local sample.
Quick question on one of the sources that is moving in the global cluster. You show the HST image, but generally it's towards the global cluster is supposed to be resolved into stars at this distance. Why is it a point source?
Well, I'm not sure that actually is a point source.
I mean, it should be resolved into stars. Like it's really at 5 megaparsec or 3 megaparsec, you just break down.
Maybe.
Question? I have a curiosity.
Yeah.
You showed, well, first of all, you mentioned that you removed all the ones that had a count, that had a detection in another mission. But if, for example, is it had a disruption events, you expect maybe some sustained emission. So the afterwards comparison with the properties of theta disruption events. I mean, I was expecting not to find anything because in case you're cutting away those.
Well, I mean, so if it's an IMBH white dwarf, then you might only expect it to be relatively short and not necessarily have much repeating, right? If you have a supermassive black hole, you might have a longer term sort of effect.
You could have both. You could have either like a sustained like decay which does not go down as the typical minus factors. But okay, we can discuss. But also you can have like a surviving object that gets streaked repeatedly, for example.
I mean, yeah, I mean you can, and we would have thrown those out effectively. So I have a student who was supposed to go back and look at the ones we threw out and see if we can find any interesting properties with them. But essentially, if they end up being in objects that are extragalactic, resolved galaxies, that is definitely very interesting. Right? But for the first pass, we have a lot of contamination from stars, and so we wanted to kind of remove those in the easiest way, and that was just a sort of draconian cut because we don't have great imaging over much of the sky. Right? Very recently, we have decals or legacy survey, which goes to 23rd magnitude in many places. So that's not bad, but there still are going to be some fainter stars that can show flares and
Nice talk, Franz. There's a whole mine, a field to be mined that I hope but I'm okay with that. And that is jetted TDEs, which you mentioned a couple of times. And I think most of us in the room will remember the very first TDE was very likely a jetted event. It was a hard event. It was mistaken as a gamma ray burst. And then all the action, became more clear. So that's really probably because only BAT and integral and PBM are burst wide field sensitive. And the question could be rephrased as what would it take to discriminate the gamma ray burst from a jetted TDE? And that would probably be a spectral difference in both cases.
I don't know. I mean, I think the
It's
the
not
energetics, if you integrate the energetics over a decent amount of time,
Yeah.
the DRB probably is going to have to drop off. Whereas the jetted TDE might sustain itself for longer. It will be repeating. But that's what we see in the few jetted TDE cases.
It would be followed, so a gamma ray burst followed by a soft event that lasted for days.
Yes, but there could be, I mean, the issue is there could be a lot of intermediate things,
Yeah.
right? And they may have properties which would be difficult to pin down. And that's the problem with relativistic beaming in the first place, right? You're going to have all sorts of intermediate weird variability and spectral changes that you might see.
Okay, so let's start speaking again.